Voice wins. So welcome to Math331 problem solving. Hopefully this is lecture 9. So what we've been doing for the past couple of days is we've been doing generating functions. And we have been very fortunate in that the problems we've looked at have had generating functions that have nice closed form expressions. And from those closed form expressions, bless you, we can deduce a tremendous amount of stuff. We got Benet's formula for the Fibonacci's. We got an explicit formula for the Catalan number, 1 over n plus 1, 2 and choose n. This is very misleading. Most of the times, if you take a sequence and create the generating function, you have a mess. And you have something that does not have a nice closed form expression. So what I want to do today is show you that while this works for a variety of problems, for other problems, it just reduces it to something you can't do. Now, with a little bit more work, you can sometimes still extract useful information from it. So what I want to do is talk about some of the applications of generating functions to some problems in number theory, to some problems in counting. And what is strange is that certain problems turn out to be tremendously difficult. So we have some backdoor approaches to get the answer. So we saw the triangle game earlier, where we had a prospective student who was excited about having a chance of not only getting into Williams, but getting free tuition, and then we crushed his hopes, right? Just of getting the tuition paid for, not of getting into Williams. Right? How did I know I would win against him? How did I know when I played the triangle against him that I would win at the end of the day, no matter how I played?
You had a winning strategy.
Well, my winning strategy was to play. Why was my winning strategy just as simple as to play? This was where I needed to make sure there was at least one triangle labeled 0, 1, 2. And what do we know about the number of 0, 1, 2 triangles? It's odd. So since it's odd, it must be at least one, therefore it must exist. This is actually a terrific way of proving the existence of something. You prove that the number of such objects is odd, therefore there must be at least one. How many of you have heard of Dirichlet's theorem? He's one of the people who has lots of theorems of primes and arithmetic progression. So if A and B are relatively prime, let's let pi x a b equal the number of primes less equal to x such that P is congruent to A mod B. Okay? Why do I assume A and B are relatively prime? Yes?
Otherwise A mod B would be 0.
Not necessarily 0.
But
You're close. So let's say we want to find primes P congruent to 3 mod 12. How many primes can be congruent to 3 mod 12? At most 1. If these two numbers share a common factor, there's going to be at most 1 prime, whatever that number is. It's not an interesting problem. So the problem only becomes interesting if A and B are relatively prime. So the deep theorem is that there are infinitely many primes congruent to A mod B as long as A and B are relatively prime. You could ask an easier question. Is there at least 1 prime congruent to A mod B if A and B are relatively prime? There's been a recent advance in the past few years. I have to define terminology. Elementary does not mean easy. Okay? When a mathematician says, oh, that's elementary, that basically means we're not using complex analysis and other subjects like that. It doesn't mean that the argument is not subtle or that you don't need a great insight to see how to do it. There is an elementary proof of the prime number theorem. So the prime number theorem, not surprisingly PMT, is that pi of x is approximately x over log x. This is proved by using complex analysis. It can be proved without using complex analysis. For years, people thought that the only way it could be proved was with complex analysis. And in fact, a lot of the results in complex analysis were motivated by people trying to study this. and then in 1896, Hadamard and de Villers-Poussin both came up with proofs heavily using complex analysis. And eventually two conjectures emerged. It is fundamentally a statement about what's called the Riemann zeta function and complex numbers, and you need complex analysis to prove it. Or, if you could somehow prove it without complex analysis, boy, would you know a lot. As of today, both statements are false. There is a proof that doesn't use complex analysis. It gives a much worse result. It does not really highlight what's going on. Just some really nice operations with logarithms. It turns out that pi of x a b is approximately equal to pi of x divided by phi of b. So this is the number of numbers relatively prime to b. Has everybody seen the torsion function? Okay, so phi of n is the number of integers less equal to n and relatively prime to n. So phi of a prime would just be the prime minus 1. Phi of 12 would be 4. 1 works. 2 does not work because 2 shares a factor with 12. 3 shares a factor with 12. 4 shares a factor with 12. 5 does not share a factor with 12. 6 shares a factor with 12. 7 does not share a factor with 12. 8 shares a factor with 12. 9 shares a factor of 12. 10 shares a factor with 12. 11 does not share a factor of 12. And 12 shares a factor of 12. So there would only be 4 numbers relatively prime to 12. What this is basically saying is that to first order, the primes fall evenly in the residue classes, in the congruence classes. That to first order, there's no bias. And until very, very recently, the only way we knew how to prove the existence of one prime congruent to A mod B is to show not only there are infinitely many such primes, but to first order they all fall evenly among the congruence classes, therefore there's at least one prime. This is ridiculous overkill. But sadly, this is often the only way we know to solve problems. You want to prove something happens, you show it happens an enormous amount of times. Therefore, it must happen at least once. Any Spaceball fans here? Spaceballs, the movie? If so, how good are you with your lines from Spaceballs?
I don't know any at all.
I will not then do the line from Spaceballs. But this is one of our most powerful proof techniques. So I want to show you how you can use generating functions to attack certain problems. We will be able to see how some of them might actually even be solvable and just get a sense of what are the difficulties. So a lot of these problems were initially felt to be beyond what mathematicians could do. These were just not problems you should study. When you think of primes, what operation do you think of with primes? If I give you a bunch of primes, what do you want to do to them? You want to multiply them, right? Why do you want to multiply? Well, because every number can be written uniquely as a product of prime powers. And if you say that the primes have to be written in increasing order, that's what you need for the uniqueness. I really don't want to consider 2 times 3 different than 3 times 2. So every number can be written uniquely as a product of primes. Primes were meant to be multiplied. These are our atoms for numbers. We break up complicated numbers into the primes and build them up. You could add primes. You are welcome to do that. And then you can ask, if I add primes, what do I get? And so this was a big conjecture. So go back. For all n big, I'll do 2n big. 2n equals p1 plus p2. So every sufficiently large even number can be written as the sum of 2 primes. And for all 2n plus 1 big, 2n plus 1, p1 plus p2 plus p3. I can write every sufficiently large odd number as the sum of 3 primes. Anybody want to guess what big is here? Yes?
Not 2.
Not 2. Yeah, when you did it like this, if you had just had one finger less raised, that would have been the answer. So the conjecture is 4. Anybody want to guess for here? try. 7. And that's actually a theorem. So one of my colleagues from grad school was the one who finally finished the proof of this. So you can check small values by brute force, and then there's ways to attack far, far down. Now, instead of writing things as sums of primes, I could write things as sums of squares or sums of cubes. And you get, from our last theorem, x to the n plus y to the n equals e to the n. The only solutions of this that are non-trivial have n equal 1 or 2. And by non-trivial, I mean if I take y to be 0, it's not that hard of an equation to solve. In fact, I can find infinitely many solutions when y is 0. So we don't really want to count something like that. So the question is, how do you attack something like this? The primes are defined multiplicatively. We want to attack an additive problem. And while we're doing primes, you could do instead squares or cubes. And so another question might be, is every integer sufficiently large a sum of 2 squares? So first of all, is every integer a sum of 2 squares? So give me an integer which is not a sum of 2 squares. 3. Okay. So note 3 exists. Okay. So we know we can't do every integer, but maybe 3, and there's maybe a few other really bad ones. And once we go high enough, then we've hit the limiting behavior. So we're going to give a couple of proofs of this, that there are in fact infinitely many numbers that can't be written as a sum of 2 squares. Can you give me another number that can't be written as a sum of 2 squares? I'm sorry?
4. Yeah, 4 and 0.
So we will consider 0 a square. But it's an interesting question as to, do you want to allow yourself to have 0? So we are not allowing 0 as a prime. We're not allowing numbers to be a sum of just one prime.
7.
Okay, so 3, 4 is good. Is 5?
7.
4 and 1. 5
Okay, so 4 and 1 gives us 5. What about 6? So we can't do 6. 7. 8. We can do 8. 9. 10. 11. 12.
Sorry, wait, 9?
9 and 0.
3 and 0. Oh, yeah. Yes. Okay. What do you have against 0? It's done nothing to you.
I don't like 0 squared.
Oh, you don't like 0 squared. Okay.
Well, 12 doesn't work either.
I'm sorry? 12 does not work. All right. So we're getting a lot of failures. 13.
Yeah,
9 and 4. Okay. 14. So I think 14 probably also. So there's going to be a lot of failures. So one thing to do is start gathering data and try to get a sense. Do you think there are any certain types of numbers that might fail in being written as a sum of 2 squares?
Well, I feel like anything that would require the previous, let's say after you got to the highest one, and
Right.
the difference between is any number that's already on there, then it doesn't work. Or 3, essentially.
But the problem is we have lots of other numbers we can play with. So if we use the largest number, we could then use maybe 2 medium numbers next time.
Oh, yeah. Okay.
So that unfortunately makes things a little bit harder. So one thing is to try to figure out what's the right, yes? Oh, okay. Did you have a comment or no? Okay. So one thing is to try to look at maybe what types of numbers. Well, let's say x is a square. So x is y squared. We want to look at what kind of numbers can be written as a square. And let's look at their remainders. So what do you want to look at their remainders mod? We need to choose a good thing to look at them. So if we do it mod 2, then we're just asking, are you even or odd? We could do it mod 3, but mod 4 is actually very good. Look at this mod 4. So if y is in 0, 1, 2, or 3, then y squared, 0 squared mod 4 is 0, 1 squared mod 4 is 1, 2 squared mod 4 is 0, and 3 squared mod 4 is So if you look at the numbers mod 4, if you're a square, then you're either 0 or 1 mod 4. So if I sum two squares, so y1 squared plus y2 squared mod 4, what does that have to be in? What are the possible values of the sum of two squares mod 4?
0, 2.
I'm sorry?
0, 1, or 2.
0, 1, or 2. So that's enough to show that we miss at least 25% of numbers. Yeah, maybe we can do better, but this is enough to show miss at least 25%. Yes?
Can I ask, how would you have known to just do mod 4?
A lot of it is experience. It's trying to say, I've got two numbers, and I want to look at what can I say about them. So a lot of times in problem solving, it's what kind of congruences can you have? And just trying to get a sense of which things can and cannot work. So here, this is enough to show us that you miss at least 25%. I want to show you another way to prove that you miss a positive percent with sums of two squares. Now, if we tried to do sums of three squares, then we would actually have all possible congruence classes. And so you might think maybe every number is the sum of three squares. It isn't. And then you would try to think maybe instead of looking at mod 4, what might be good to look at? So mod 4 will not be enough if we want to look at sums of three squares. What might be good to look at mod? 5 is one possibility, or 8. I think 8 is better because it's building on this. So if we did, let's do that quickly. So mod 8, you've got 0, 1, 2, 3, 4, 5, 6, and 7. But 7 is the same as negative 1. 6 is the same as negative 2. 5 is negative 3. And 4 is negative 4. Right? So when I square things, 6 squared is the same as 2 squared mod 8. Because the minus sign just reinforces. So if I look at y squared mod 8, that's going to be in 0, 1, 4, and 1. So those are only the possibilities. So y1 squared plus y2 squared plus y3 squared mod 8. What are the possibilities? Well, I could have 3 zeros. I could have 2 zeros and a 1. I could have a 2. I can have a 3. I can have a 4. I can have a 5. I can have a 6. And that's it. So you miss at least 12.5%. So you miss anything that's 7 mod 8. So this is, again, a very common technique, is to try to see, are there certain types of numbers that will fail, that will not have a good representation. And so this is enough to prove that I can't write everything as a sum of 3 squares. It turns out it's a theorem due to Lagrange. Every number can be written as a sum of 4 squares. This is a very popular colloquium topic. And there's even a formula that tells you how many ways there are to do it. All right. What I want to do is I want to step back and show another proof that you can't write every number as a sum of 2 squares. And this is a counting argument. And I really love these counting arguments. So hopefully you've learned by now, I love looking at extreme cases. I love saying, let's assume everything goes our way, or let's assume everything goes against us. What can we say in situations like that? So let's try to write all integers up to x as a sum of 2 squares. So we want to write n as, say, y1 squared plus y2 squared. And we'll look at all n less than or equal to x. And the goal is to show that there's going to be a lot of n, in fact a positive percent of n, where you can't do this. Okay? Well, I've got two numbers y1 and y2. What can you say about their relative size? Without loss of generality, what can I assume?
y2's bigger.
y2's bigger. 0 less than equal to y1, less than equal to y2, less than equal to 2. And how large can y2 be?
N.
I'm sorry?
N.
You can do much better than n.
Root n.
I'm sorry? Square root of n, or actually square root of x. If I'm trying to write n as a sum of two squares, and n is at most x, I better not take one of these numbers to be larger than the square root of x, or I am immediately out. Okay, so I now want to count how many pairs of integers are there where y1 and y2 are at most square root of x. Well, I have two cases. I could have y1 equals y2, and I could have y1 strictly less than y2. How many pairs are there where y1 equals y2?
1.
Not one. Just how many pairs of numbers up to square root of x?
Root x.
Root x. Technically, it's not root x. You have to be a little bit better. So technically, it would be the floor of root x, and it's not quite the floor of root x. We have 0 as well. So, but it's bounded by, at most, square root of x plus 1 pairs. Over here, how many pairs do we have? I need to choose two distinct numbers. y1 is at most, y1 is strictly less than y2.
X over 2.
Yx over 2.
Because
It's close to that.
and you have oh no, x times x plus 1 over 2.
Okay, not x.
Right.
Root.
This is a binomial coefficient. It's
Root
essentially
x.
root x plus 1 choose 2. I have, assume root x is an integer. I have root x plus 1 integers. I need to choose two of them. If I choose two of them, they'll be distinct. The larger one becomes y2, the smaller one becomes y1. And this is essentially, square root of x plus 1, square root of x plus 2 over 2. This is approximately x halves. If you want, the next term will be of size 3 halves square root of x, and then the last term will be plus 1. That'll be an upper bound. So if we add this to this, so total is going to be less than or equal to x halves plus an error of size square root of x. So if you look at how many numbers you can represent, you can only get 50%. This is better than the mod 4 argument. Right? The mod 4 argument showed that we lose at least 25% of numbers. This shows that we lose actually at least 50% of numbers. Well, technically not quite 50 because we've got that small error term, but in the limit it's insignificant. So just by looking at how many pairs do we have, and this is a really common argument, we get that we miss at least 50% essentially of all the possible numbers. What we're assuming now is whenever you take two numbers, assume that the sum of their squares does not equal the sum of any other square. And then in that case, the most numbers we could represent would be this. So is that the case? Are there ever two sets of numbers that the sum of their squares equals the sum of other squares? Can you give me two different pairs of numbers that have the same sum of squares? And this is related to a book that I'm refereeing where I think the book is wrong. You give me two different pairs of numbers. So I want a squared plus b squared equals c squared plus d squared.
Can C and D be the same number?
C and D could be the same number.
So 7 and 1 versus 5 and 5.
Okay, so 5 squared plus 5 squared is 7 squared plus 1 squared. That's a better example than mine. Mine was 3 squared plus 4 squared is 5 squared plus someone's least favorite number, 0 squared. This is a better example because this is a non-trivial one. Everything is non-zero. Right? So I will give you more credit for that than my example. So I was just referring a book that said if you have a right triangle, there's no way to choose it so that both the leg and the hypotenuse are integers. 3, 4, 5, 5, 12, 13. In fact, there's infinitely many ways of doing this. So, but okay, so you do agree that such triangles exist? Okay. Years ago, there was a special in Massachusetts on teachers who make a difference and are really good. And there was a 4, 6, 10 triangle in the background. If you have any triangle, what do you know about the sum of the lengths of any two sides? It's greater than the third. You have the base over here, and if the sum of the two other sides is the same, then as you start moving up, they can no longer connect. So, all right. So these are really simple arguments to show you when you can't do something. All right. Then the question becomes, well, how do you prove that you can do something? And again, one of our most powerful techniques to prove you can do something is you prove you can do it so many ways. You must be able to do it at least once. So what I want to do is I want to show you how would you attack a problem like this. And the idea is to pass from knowledge of calculus or analysis to the problem we want to study. You've taken all these advanced math classes. Hopefully there's a reason you've taken these advanced math classes. Hopefully this material can be used for something. They have changed the curriculum a little bit since I was a child. Okay, I believe nobody does graphing by hand anymore in Calc 1.
No, we do.
You stay away from that, okay. I believe, wait.
We do. We do graph in Calc 1. By hand.
By hand.
By hand?
Yes.
Yeah.
We even Williams Calc 1 they do that.
Okay, let's change the topic of
I I'm TAing it.
Alright. When I was young, shortly after the dinosaurs vanished, we were taught how to use tables of logarithms and tables of trig functions. Please tell me you are no longer learning how to use tables of logarithms and tables of trig functions to evaluate logs of numbers and sines of angles.
Wait, what'd you say?
That.
We actually had tables, and if you wanted to calculate the sine of 3.27 radians,
You just the circle. You talking about the circular table?
just tables with numbers.
We had
You know,
that.
0.01, 0.02.
Oh yeah, I guess we're a little more sophisticated. We have a circle now.
Oh, you have a circle with a couple of special values.
Yeah.
Right, but that's only to do like the sine of 30 degrees or the cosine of 45.
You're saying they literally just had tables of random values.
Not random values, ordered values, all values. So if you wanted to do the sine of 1.3, you would just go to your table and you would look it up.
That's a waste of
We
paper.
did have this in the back of our books that we
Right. And then there would be ways to interpolate. If you needed a number that wasn't between, if you need 0.015, how would you weight those two values? There is a reason why this is no longer really taught. All right? This is the 21st century. We have calculators. We have computers and tables that just have this now all built in, and they will return it. So I want to show you how you can actually attack a problem like this. So we're going to define a general function. Let's let fn of x be the sum p less than or equal to n of e to the 2 pi I px. And e to the I theta is cosine theta plus I sine theta. The first year I was at Williams, 1/3 of my senior seminar had never seen e to the I theta. So I am not assuming people have seen e to the I theta. Who here has not seen e to the I theta? Okay, so I see at least 3 hands that are up. How many people are very comfortable with e to the I theta? Okay, what this means is there is a gap in your math knowledge. This is, again, one of the only classes where we can fix gaps like this. And so we're going to now do an aside and talk about e to the I theta, because this is something you should know. This is one of the most important functions in mathematics. You might remember from years ago in high school, de Moivre's theorem.
I remember the name.
Yes. It's like, how do you get formulas like cosine n theta? I will teach you all of trigonometry in a minute.
Yay.
Okay? So, again, we have the ability to do these digressions. How many of you can prove the double angle formula for trigonometry right now if your life depends on it?
No.
The double angle formula or the angle addition formula. I'm going to be very careful because this is being recorded. I am concerned that there is somebody going around campus right now who will be... All right, so... You have to be extremely careful how you phrase things. All right. How many of you have seen this formula? N goes from 0 to infinity, x to the n over n factorial, the formula for e to the x. Has everybody seen this? I'm sorry?
At some point, yes.
At some point. So this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. How many of you are econ as well? Is anybody here econ as well? You might have seen this as the limit as n goes to infinity of 1 plus x over n to the n, coming from compound interest and going to compounding at a instantaneous process. And this would give you an interest rate of essentially x. And it's a nice exercise to show that these are the same. This is the series expansion for e to the x. This is what we mean. What is e to the x times e to the y? Yes, but you don't know that. What is e to the x times e to the y? Yes, it is technically the sum, n goes from 0 to infinity, of x to the n over n factorial, times the sum, say, m goes from 0 to infinity, of y to the m over m factorial. If this did not equal e to the x plus y, then we would have horrible notation. What's 1 over sine? Yeah, cosine. We've got bad notation. So mathematics does sometimes have bad notation. It would be terrible if this was not e to the x plus y. It turns out, I'm not going to justify all the steps. I'll leave this as an exercise for you. This is the same as the sum k goes from 0 to infinity, the sum L goes from 0 to k, x to the L, y to the k minus L, over L factorial, k minus L factorial. And the reason this is true is if I take 3 powers, let's say I want to take k to be 7. How many ways can I get, when I multiply this, a term that has degree 7? I could have no x's and 7 y's. I could have 1x and 6 y's. I could have 2 x's and 5 y's. So if I want to have the product of degree k, if I take L x's, I take k minus L y's. This should remind you of the convolutions we did previously. It's all related. And so this is another way to write the sum. You must be careful whenever you have infinities going on. You have to be able to justify interchanging. I won't justify this, but because x and y are fixed and n and m factorial grows so rapidly, this can be justified. Now it's down to pattern recognition. You have an L factorial, a k minus L factorial. This should be screaming something to you. What does this look like? It's not quite, but it's close to something. Yeah, it's close to a binomial. What would you love to have? What is this missing? You've got a L factorial, k minus L factorial. What do you want to shove in here?
K
a k factorial. So let's just do that. Let's shove in the k factorial. And so now we get that this would equal the sum k goes from 0 to infinity. I'll put the k factorial outside, and then inside we'll have a sum L goes from 0 to k of k factorial divided by L factorial k minus L factorial x to the L y to the k minus L. Well, this is just the binomial coefficient k choose L. And now by the binomial theorem, this is the sum k goes from 0 to infinity of, this just becomes x plus y to the k over k factorial. This is the binomial theorem. And then, by definition, that becomes e to the x plus y. So this is a proof that e to the x times e to the y is e to the x plus y, at least if x and y are numbers. If x and y are matrices, it's far more complicated. It's only true if the matrices commute. But this is the justification of why we write it this way. We want to think about powers. All right. So what I want to do now is just review a little bit of Taylor series for you. So you might remember cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus yada yada yada. And you might remember that sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus yada yada yada. And then it's either I is or I am the square root of negative 1, right? We all remember this. I is the square root of negative 1. What's I squared? Negative 1. I cubed. Negative I to the 4th. And it just cycles. So if you look at e to the ix, you get a sum, and it goes from 0 to infinity, of ix to the n over n factorial. And now notice that every time n is even, we'll have I to an even power. It'll be either 1 or negative 1. Every time n is odd, we'll have I to an odd power, and it'll be either I or minus I. And so when the dust settles, you will get that this is cosine x plus I sine x. So I'll let you do the rest of the algebra here. Okay? And you can begin to say, oh, when n equals 0, I'll get 1. When n equals 2, I'll get a minus x squared over 2 factorial. When n equals 4, I will get a I to the 4th, which is 1, so I'll get an x to the 4th over 4 factorial. So this is essentially a proof that e to the ix is cosine x plus I sine x. Okay? So I'm going to state the results that I need. So e to the ix is cosine x plus I sine x, and e to the ix, e to the iy is e to the I x plus y. So how many of you have seen the connections between the exponential function and the trig functions? So the exponential function has a really nice addition formula. E to the x, e to the y is e to the x plus y. The trig function sine and cosine have angle addition formulas. There's connections. I think I can do this, but I don't want to. Here's my unit circle. I feel like I'm a little teapot. All right, here is, say, my angle x, and then I draw another angle y, and I want to calculate what is the, say, sine or cosine of x plus y. I'd be dropping something down like this, and then what I can do is I can start playing games. And if I wanted to calculate the sine, I would need to figure out what is this length. If I want to calculate, this would be the cosine, this would be the sine. Well, if I can figure out what this length is here, there's so many different lines I can do. If this is x, this is 90 minus x, this is 90 minus x, this would be x up over here, correct? This would be 90 minus x, and you can start playing all these different games as to where do I want to go. And so let's see which is the best way to do this. So I can calculate this right angle here very easily. I'm sorry, this side over here, because I've got a right triangle, radius 1. So this length over here would just be the sine of y. And then I would want to maybe, so the question is, which of the lines do I want to do this at? So I think I want, okay, so I just want this one over here. So is this a right angle over there? Yes, this is right. So this would be 90, okay, so this would be 90 minus x over here, right? And so this would be x over here. So this line over here is going to just be the sine of y. I'm sorry?
Why is that 90 minus x?
Because this is a right angle over here. I drop a right angle from here down. So I drop an altitude from this point here, and I make that a right angle. So it's probably, so it's a bad picture, so I'll draw a better picture. It should not be hitting the circle. So it should be like this. Yeah, it was a bad picture. The picture sucked. And now this is a right angle. And so if this is x, 90 minus x, 90 minus x, this is x, 90 minus x, so this is x over here, right triangle. So this side over here, this hypotenuse, it's a 1, so this is just going to be the sine of y. This over here, it's the hypotenuse times the cosine of x, so this length here is sine of y, cosine x, sine of y. And now I want to get this length over here. Well, this length over here, this hypotenuse, is going to be the cosine of y. And then to get this, it'll be cosine of y sine of x. So this whole length here, now it's going to be cosine y sine of x, and this will be the sine of x plus y. So just not written in the standard form, but there's a proof of the angle addition formula for sine, at least if all the angles are less than 90 degrees. And then you can just use properties of trig to extend beyond. So you've got to draw a picture like this and argue. It's not a fun picture. We've got 5 minutes. This is more than enough time to teach you all of trigonometry from these two facts. What's the big theorem of trigonometry in terms of sines and cosines, the big relationship? Sine squared plus cosine squared is 1. Excellent. E to the ix times e to the minus ix is e to the 0, and e to the 0 is 1. I mean, I could do this in a minute, but I'm heavily medicated because I have a cold, so I'll do it slowly. This is cosine x plus I sine x. And now we have times cosine x plus I sine of negative x. Well, the sine of negative x is just negative sine x. You can see that because sine is an odd function. And now when you expand things out, you get cosine times cosine is cosine squared x. I sine x, cosine x, minus, the cross terms cancel. And then you have a minus I squared, which is plus 1. So cosine squared plus sine squared is 1. Here's Pythagoras coming from e to the ix. All right. Any questions on Pythagoras? Let's prove the angle addition formula. So now, let's look at e to the ix, e to the iy is e to the I x plus y. So here we have cosine x plus I sine x, cosine y plus I sine y is cosine x plus y plus I sine x plus y. And now all we have to do is expand things out. So we get cosine x, cosine y. This is going to be imaginary, this is going to be imaginary, this is going to be real. So I'm going to just keep all the real stuff together. I times I is minus sine x sine y. Plus the imaginary parts, I'll have sine x cosine y plus cosine x sine of y. The only way two complex numbers can be equal is the real parts are equal and the imaginary parts are equal. You want to know what cosine x plus y is? There it is. You want to know what sine of x plus y is? There it is. There's your angle addition formulas. All of the trigonometry comes from this. And this is why you have certain relationships for sines and cosines. This is where it's coming from. It's coming from the exponential function. It inherits it from the exponential function. You can even write, I'll erase this. And then I'll end with a foxtrot joke. So you can write cosine of x as e to the ix plus e to the minus ix over 2. And you can write sine of x as e to the ix minus e to the minus ix over 2i. So this is a way to write sines and cosines in terms of exponentials. How many of you have seen hyperbolic functions? So this is where you get the hyperbolic functions. You just replace x with ix. And so you get hyperbolic cosine is just cosine of ix. It'll be e to the x plus e to the negative x over 2. And the relation you get is cos squared minus sin squared is 1. What can you tell me about values between of sines and cosines? What are values of sine? Yes?
Between -1 and 1.
Between -1 and 1. And there was a great Foxtrot comic strip where one of the people goes, lousy camp calculator, it's giving me, the cosine is 3.2. Anybody knows the cosine can't be. And they're looking at, oh no, you've got it in hyperbolic mode. And then his other friend says, if you want, you can have my calculator. Some of us don't need them. All right, so we will continue and show how you can use these to actually talk about how can you write numbers as sums of primes or sums of squares. This is just really good background material we need. If you haven't seen it, again, we have the freedom to do that in this class.